As I suggested yesterday, the next thing that will come after just a regular spanning tree is the idea of a minimum spanning tree. So this is only going to happen in a weighted network. I should be able to highlight, but that's not working. That's only going to be able to happen in a weighted network because the idea then is that we actually have to decide. Our spanning trees from yesterday were a bit random. We could just use any edges we wanted. We now have the additional challenge that with these weights on the edges, we need to find the cheapest spanning tree that we can construct, the one with the lowest numbers. So before I show you some tricks, what I want you to do is pause the video, have a look at these networks. This one, I think you can probably work it out just by gut having a go. This one might be a little more tricky, but have a go without any advice. Pause the video, copy it down, and see what you can work out. And then when you think you've got an answer, we'll have a go at these together. Pause now. So how are we going to do this? Well, what I want to do is just highlight some pieces. So if we start in this, let's just start anywhere. Like if I start up here, we've got a 4, a 4, a 4, and a 3. I guess it makes most sense to use the 3. It may look like then this would be good, or this, actually, if we're over here, well, the 2 looks like it's the best option for us. And if we've got all of this connected, do we want to join up our halves with a 4, a 5, or a 3? I'd go with the 3 because it's smallest. So there's our minimum set. And we would make a copy of what we've got underneath. If I can get my stylus to line up. I've got 1, 2, 3, 4 with 3, 3, and 2, which means our weight is only 8. Did any of you do better than 8? Well, I'll never know. With this one, I'll have a go. Again, sometimes the fun thing to do is to just, well, I know the algorithm, so it's hard for me to think about this. We have to have this side. That's obvious. And I would say that that's probably useful. Well, we've got to get to these points anyway, so the cheapest one has got to be included. I would suspect that the 4 is going to get used because it's the cheapest way to go there. And this 6 seems cheap, but maybe 5 is better. And hey, there we go, and with the 7. Now, I've kind of just gone around in a randomish order. I know that I've got the smallest one. You guys might not be 100% convinced. So, again, we can redraw. And we went up to here, down to there, across to there, and up to there. And I believe that that's the smallest one. Again, if you guys think you have beaten me, show me one with a smaller weight. 10, 21, another 9 makes 30, 37. So a total weight of 37. So, thankfully, for those of us who found this a little awkward trying to guess at what the right moves were, and I mean, we could have made some wrong moves. We could have tried it a couple of times until we found the right solution. I just didn't want to waste time on the video doing that. If we scroll down a bit, I will show you there's actually 2 different algorithms. And what's most amazing out of all of this is that both of these algorithms, using very different methods, end up with the same result. Prim's algorithm starts with basically a network, and you are slowly expanding that network. Kroskull's algorithm just says, I don't care, just put in any shortest edge that doesn't create a loop. So let's have a go at Prim's algorithm. I'm going to use the highlighter kind of trick here again. And we're going to start with a point. Now, given that A is called A, we might as well start at A. And I will annotate what we've done afterwards. But the first thing we can do is we can look at A as our whole network and say, where are all of the exits from A? There is an exit that goes to C, to B, to F, and I want the smallest one. So let's go join B into our network. We now have a slightly larger network. There are now 1, 2, 3, 4 ways to get out, and the smallest of those, 9, 10, 8, is 7. So we've now gotten to F. Now we look again and we say, well, what's the smallest edge we can join in to get to something new? 9, 10, 9, 3, and 6. Well, the 3 is clearly the smallest. And at this point we look again and we go, well, that 4 is the smallest. And then we look again and we go, well, there's a 9, a 10, a 9, a 7, and 8. Now I'm not looking at this 6 at this point, because 6 is only going to create a loop. It's not going to make our network any larger. So we're only looking at lines that join up to something on the outside that will be new to our network. And so that would be our finished product. Now if I get the right pen, I can write down what we did. Well, we chose to start at A. You don't have to start at A. You could have started at any point on this graph. If we started at C, the smallest thing into C is the 7, and we would have gone there first, then joined the 3 and the 4, then joined up with another 7 and the 5, and we would have been done. But let's start with A. We started from A. The first thing we did was we added the edge AB, and then we added AF. Didn't really have any choices along here. Then we added FE, then we added ED, and then we added EC. And that was, we added 5, 7, 3, 4, and 7 for a total weight of, well, there's a 10 and a 9, 26. And that was using Prim's method. Our alternative, and if I can use some magic of editing, so let's have a go at Kruskal's algorithm. This time we're going to look at it and we're going to say, well, which is the smallest edge at all? Well, it's this edge of length 3 going from F to E. We're then going to look for the next smallest edge that doesn't create a loop. Well, that's the 4 here. The next smallest edge is over here, AB with 5. The next smallest edge technically is FD, but that would create a loop, a cycle, and we don't want to create any loops. So the next smallest edge, well, after we ignore the 6, is, well, then there's 2 of these 7s. So in fact, both of them, like if both of these connected across the same gap between our networks, we could pick whichever one we want and there would be 2 equally good solutions. But in this case, both of these are worth doing. One to connect the 2 disconnected networks together, and one to add C in as well. So now we're done here. Now that's exactly the same network we had last time, but drawn in a different order. So using Kruskal's, we first have FE, and we added in ED. We added, well, we added AB. We ignored FD. And then we put in AF and CE. So again, but this time it's 3, 4, 5, 7, and 7. Well, the weight adds up to, again, we've got a 10, a 9, and a 7. We have 26. It's the same sides. It's going to be the same weight. So that's enough for you guys to have a go at exercise N2.2.2. And because this is the end of the 2.2 section, there is an assignment again, one of the slightly longer tasks that looks at the work from yesterday and today, and I definitely need to see evidence that you've done it. Ideally, let's get this done by the end of term and get it sent to me before the holidays so that we're all square, ready to move on at the beginning of next term. Now, there is more network stuff we're going to look at next term, but the plan will be, again, this Wednesday as our last lesson of the week, we're going to do a live catch-up meeting where you guys can ask for help and we'll go through as many questions as you need from any of the topics.